Hey, ladies and gentlemen. Hope you're studying. So, before winter break, we started a topic on predicting reactions. We have a practice quiz that was handed out in class. I'm going to go over the answers to the practice quiz, how to solve these problems, and you can listen to this one time, a million times, however many times you need to, so that you can understand it. Also, a lot of these questions on the practice quiz, they're similar questions on worksheets 1, 2, 3, and the review sheet in your purple packet. Feel free to practice there. We'll post the answers to some of those as well. Some of the questions in the review sheets and the practice sheets are a little bit harder than what you need to be able to do. So we're just going to kind of go over the basics. If you can do these questions, you will be ready for your quiz/exam. So the first question on the practice quiz was about solubility in dissolution or dissociation equations. First of all, these compounds, ionic compounds, can dissolve in water sometimes, and other times they don't. And it just depends on how attracted they are to water. And it's virtually impossible for a person to predict based on just the formula whether or not it would dissolve. So scientists have repeatedly tested hundreds and hundreds of compounds, and then they just listed the results, and they put them in a set of rules, which we call the solubility rules. And these solubility rules are found on the back of your periodic table. So you're going to need your periodic table. Pause the video if you haven't got a periodic table out. Alright, good. You got your periodic table. Now all you do is you look up these compounds on this list. So potassium fluoride. This one's going to be soluble for two reasons. First reason, let's go right here. All fluorides, this is rule number 4. It says all fluorides are soluble except when combined with lead. Potassium is not lead. The other reason it's soluble is potassium is an alkali metal. If you don't remember on the periodic table, oh, look at this great periodic table. The first column on the periodic table is the alkali metals, is group 1. So potassium is soluble and fluorine is soluble, so this one's soluble for two reasons. We actually needed it to be soluble for one reason, but we got two. So let's just write S-O-L-U-B-L-E, soluble, right there. Next one, chromium 3 hydroxide. Hydroxides, let's see, right there. Oh, here we go, rule 6. All hydroxides and sulfides are insoluble, except for those of rule 1 in magnesium. So we go back to rule 1. Alkali metals, aka group 1, and ammonium are always soluble. So, is chromium in group 1? No. Since chromium's not in group 1, this compound will be insoluble. So what would this compound do in water? Nothing. It would stay a solid. It would be very, very boring. The next rule, the next question, calcium phosphate. Calcium phosphate. So we're going to look down our rules list, and phosphates are all the way down here in rule 7. Kind of went off the screen, but you should be looking at your periodic table. And it says all sulfites, carbonates, chromates, phosphates are insoluble except for those of rule 1. Again, that pesky rule 1. Come back up here. Alkali metals, ammonia, always soluble. Calcium is in group 2, not in group 1. So this one should be insoluble. And the next one, gold 3 nitrate. Can you get gold to dissolve in water? The answer is yes. It's a nitrate. Nitrates of gold and nitrates of anything will be soluble in water, because rule 2 says nitrates, chlorates, perchlorates, and acetates are always soluble in water. So soluble. So those polyatomic ions, nitrates, chlorates, perchlorates, and acetates, are really, really attracted to water, and they break off from whatever they were attracted to. So gold nitrate was attached to itself as a solid, then it gets put into water, and the nitrate's more attracted to the water than the gold, and it breaks away. And so now we need to write dissolution equations for the ones that are soluble. We only have 2 that are soluble, and I kind of have sample versions of those right here. So let's first write the formulas for both of these. Potassium is a +1, fluorine is a -1, so this compound would be KF, and it would be a solid. And then gold 3 nitrate. Gold, the Roman numeral tells me what the oxidation state or charge. The charge, let's call it charge. Proper term is oxidation state. We'll call it a charge. Gold is Roman numeral 3, so it's a +3. There's our nitrate. So the formula for gold 3 nitrate is AuNO3, 3, and it's a solid. Then these 2 solids get dumped into some water. When they get dumped into water, since they're soluble, they will break apart into their ions. So let's break these 2 apart into their ions. The potassium, +1, is now separated from the fluorine, -1. And now that they're in water, their state of matter is aqueous. With the other one, the gold, that is a +3, is separated from the nitrates that are a -1, and they are aqueous. Let me erase this here so that I can slide my aqueous into there. Hey, Mr. Murphy. Yes, random student questioner. I notice that you have 3 nitrates over here, but only 1 nitrate there. Let's put a 3 in front of the nitrate so that it's balanced, because the law of conservation of mass is awesome. Now, because we have to keep everything balanced, we can't lose nitrates in the dissolution process. So, there we go. Is it soluble or insoluble? Hey, use the solubility rules on the back of your periodic table. Insoluble compounds don't dissolve in water. So we didn't do anything with these 2. We just wrote insoluble. Soluble ionic compounds break apart or dissociate into their ions in water. So we have these 2 example sample formulas there for you. Okay, let's go to the next couple questions. We're actually going to skip question 2 for a minute and go to question 3, because question 3 will kind of set up question 2. We did 5 types of reactions, and I know you're probably going, mine only says A, B, C, D. Where's this E? We'll get to that in a minute. And there's letter formulas for each of them. Single replacement. In a single replacement, you have a single element replacing one of the others in a compound. Just swapping one for the other. And so A could replace B. There we go. Or A could replace C. There we go. It all depends on whether or not A is a metal or A is a non-metal. More on single replacement reactions in a little bit. Decomposition reactions. Decomposition means to break apart, and look what we're doing to these compounds. We're breaking them apart. We have a very simple AB compound like our potassium fluoride from a second ago. Usually decomposition reactions involve heat or electricity. And so it's being broken apart. Here's a more complicated one, probably has a polyatomic ion in it, and it's just being broken apart. Synthesis is the exact opposite. In fact, these are just those 2 reactions flipped around. It's the opposite of decomposition. Synthesis means to build and put things together, and here we're taking elements and combining them together. And then the last one, the double replacement reaction, we have 2 compounds, and the pieces are being switched around drastically. So A and D are coming together, and C and B, and let me just label some. So this is metal, non-metal, metal, non-metal, metal, non-metal, metal, non-metal. It always has to be a metal with a, you got it, non-metal. You can't put metals and metals together. They would both be positively charged. They would repel each other. You can't put non-metals and non-metals together. They would both be negatively charged, and they would repel each other. Sometimes we also have acid, base, double replacement reactions, and the hydrogen from the acid and the hydroxide from the base make water, and then the metal and the non-metal get together and make some sort of ionic compound. Any ionic compound we make, and I'll circle spots where we made ionic compounds on this. Here we go, there's an ionic compound. There's an ionic compound, there's an ionic compound. Here's an ionic compound. All of those ionic compounds should, when we're dealing with actual symbols of elements, be balanced with their charges. Again, so if you had magnesium and chlorine coming together on the product side, you have to think magnesium's a +2, chlorine's a -1. I need 1 magnesium and 2 chlorines. So you use those charges to make the formula on the product side. All right, let's go back to question 2, keeping in mind these simple formulas: single replacement, one element replaces another; decomposition, break them apart; synthesis, put them together; double replacement, try the new combinations of metals and nonmetals. Oh, I forgot combustion. So combustion was left off the sheet because it doesn't have a simple formula like this. It is pretty simple though. You have some sort of hydrocarbon reacting with oxygen, and it makes carbon dioxide and water. Or what if there's only a limited amount of oxygen? If there's a limited amount of oxygen, then it makes carbon monoxide. If there's an excess, it makes carbon dioxide. Both of them make water, but when it runs out of oxygen, it makes carbon monoxide instead. All right, now we're going to hop back to question 2. So these are pretty easy to figure out. Look, these compounds are coming together to make one thing. It's synthesis. This compound is being broken apart into multiple things. It's decomposition. Here we have a metal, nonmetal, metal, polyatomic ion behaving like a nonmetal. And then we switch to them, metal with the new nonmetal, metal with the polyatomic ion. That's a double replacement, by golly. That's right, I said by golly. Here we have a combustion reaction. We have a hydrocarbon, oxygen, carbon dioxide, water. That is combustion. And then E, single replacement. We have a single element kicking out another element. That's the definition of a single replacement. So identifying them is pretty easy. We're going to take double replacement and single replacement one step further. The synthesis, decomposition, combustion, we're not going to do too much more with. But the double replacement and the single replacement, we're going to take a step further. And that's what question 5 and question 4 are all about. We're going to hop on to question 4 first, because that comes before 5. They have a series of directions here. Number 1, we have a single replacement. We have a single element and we have a compound. We have a single element and a compound. We have a compound and a single element. We wrote this one the other way around just to show it doesn't matter which one comes first in the reaction, just that you have a compound and a single element. And so we might have the single element replace one of the other elements. The way we figure this out is we check the activity series. Again, you would never have this stuff memorized. Chemists have been testing metals against other metals. So on the back of your periodic table, we have a truncated list, a short list of the activity series for metals. And then below all of the metals is a very short list of the activity series for nonmetals. So this activity series tells us which elements are more reactive and will replace elements that are less reactive. So if you have a compound, let's say, here's a horrible idea. Let's say you put lead into water. I'm going to write water as hydrogen hydroxide. Lead into water. Hydrogen versus lead. Who's more reactive, the hydrogen or the lead? Well, you look at the activity series, and lead is higher than hydrogen on that list. And so, yes, it can replace the hydrogen. And then the hydrogen would be all by itself. So, question part A, is the lone element higher on the list? In this case, yes it is. If it hadn't been, we'd have no reaction. We'd be done. But yes, it is. So we switch places with that element. So I took the lead and I put it in the place of the hydrogen. Here, I'll delete this 2 and explain where it came from. Alright, so yes, I switched the place. I put the lead in the place of the hydrogen, and now the hydrogen's by itself. A new compound's formed, and the charges need to be taken into consideration anytime you make a new compound. So let's write down. Lead could be a +2. Let's just pretend it was. It could also be a +4. I'm just picking one at random here. You would be given enough information on the actual question to figure that out. But so lead's a +2, hydroxide's always a -1, so therefore should be 2 hydroxides here. There we go. Lead's a +2. We're going to come back and erase those in a minute, but for right now I'm just leaving them there. Alright, new compounds form. If the element that is by itself now, that's hydrogen, is one of those diatomics, you might write Brinkel-Hoff down or something like that, or Hoff-Brinkel, I don't know, then it needs to be paired up. So hydrogen is one of these 7 elements that hates to be lonely, so it's always H2 when it's by itself. And it's not ionic, it's just boring hydrogen. So, here we go. Should we balance the reaction? Yeah, let's put a 2 here. That was easy. What do you think the states of matter are? That's always the last question. Hydrogen is usually a gas. Lead hydroxide. How am I going to figure out lead hydroxide? I'm going to look at my solubility rules. Solubility rules. Hydroxides are insoluble, and lead is on that list. So this should be a solid. Yes, lead should not be put into water because it can dissolve it. This doesn't easily happen in water. In hot water or even slightly acidic water, it happens pretty easily, which is why we don't use lead pipes anymore, because the lead in the pipes can slowly leach out into the water we're drinking, and lead is not good to drink. So now that we've kind of done a sample question, let's look at A, B, and C. All right, A, we have the chlorine, and the chlorine is by itself. We have the compound. Chlorine's a nonmetal. Here it is. Bromine's a nonmetal. Here it is. Which one is more reactive? Which one's higher on the list? That's right. Chlorine is higher on the list. If you're doing this Dora the Explorer style, then you might actually be responding to the questions I'm asking. If you're not doing this Dora the Explorer style, at least you're thinking the answers. You don't have to say them out loud like, a 4-year-old watching Dora might. So the lone element is higher on the list. So we're going to make the new compound. We're going to put sodium and chlorine together, and then bromine is by itself. So we switch the places. Is the new compound formed? We have to use the charges. Sodium is a +1. Chlorine is a -1. So that's correct. The lone element is one of the Brinkel-Hoff. In fact, it's the Br in Brinkel-Hoff. So it can't be alone. It's got to be a 2 there. The color is going to drive my OCD people nuts. There we go. Now we should balance the equation. There's 2 chlorines, put a 2 here. There's 2 bromines, put a 2 here. 2 sodiums, check. States of matter. Salt is usually aqueous in water. Bromine is actually a liquid. That one's kind of hard to predict. If you did liquid or gas on that one, I'd be very happy. We'll talk more about that in class. The next one, copper versus magnesium chloride. Step 1, is the lone element higher on the list? Copper, magnesium. That's right. The lone element is not. Copper is lower than magnesium. These are your favorites. No reaction. No reaction because copper's lower. Copper was lower than magnesium, so nothing happens. Notice that copper is also lower than hydrogen. That's why we now use copper for our pipes, because it doesn't react with the water. So we're done with B. Now we go to C. Potassium fluoride and lithium. Lithium way up here, it's the most reactive metal. Potassium right below it, but potassium's still less reactive, so we're going to go through a list. Make the new compound, lithium and fluorine. Kick the K out. K is now by itself. Use the charges. Potassium's a +1, fluorine's a -1, so it's a 1-to-1 ratio. Is potassium a Brinkelhoff? No, so it wouldn't be like a little 2 here or anything weird. It's just K. Balance the reaction. 1 Li, 1 Li, 1 F, 1 F, 1 K, 1 K. Oh yeah. States of matter. Okay. States of matter. Lithium fluoride. I think, boom, 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 boom. Looking at my list, alkali metals are always soluble. Fluorides are pretty darn soluble. So this thing is soluble times 2. Went too far. There we go. So this is definitely aqueous. Orange doesn't show up at all. Now the potassium's by itself. It's a metal. That's by itself. What state of matter do almost all metals exist in when they're by themselves? That's right. Solids. Good job. I heard you. I know you're responding to my random questions. Good job. All right. So there we have. Sorry, got to get interrupted by announcements there. So this style question, you're going to have to figure out what the products are. Here's the setup. Here's how you run through the list. Activity series, make the new compound, states of matter, balance the reaction. And this is what we would have done had we had not been ruined by snow, 2-hour delay, snow, 2-hour delay, all that stuff. Instead, these questions will be multiple choice style, where I will give you the reactants, and then, so I'll give you like these reactants and 4 different versions of this answer. 4 different versions. What might those versions be? Well, one of them is going to be no reaction. One of them is going to be no reaction, assuming that the activity series was read or understood incorrectly. The one, of course, would be the correct answer, like we have for C. What's a bad answer? Well, you shouldn't put lithium and potassium together. That's a good bad answer. I mean, lithium and potassium are both metals, and if they have a charge, they're not going to be attracted to each other, so no. And states of matter could be wrong. That lithium fluoride better be aqueous because of the solubility rules. So you could check the states of matter also. So pay attention to the possible, you have these different possible products, but these steps will actually already be worked out. You're going to have to understand single displacement reactions enough that you can find the one that follows all of the correct rules using the activity series, the states of matter, balancing, all that. All right, let's look at number 5, the double replacement reactions. So again, I wrote the general equation here. And we have to switch the combinations around. So, I'm going to just underline all the metals in red. There we go. And then the other thing's either a non-metal or a polyatomic ion. And we have to make the new pairings of compounds. So the lead and the chlorine come together. And then the potassium and the iodine. The zinc and the hydroxide, the magnesium and the nitrate, the lithium and the chlorine, and the strontium and the nitrate. Holy cow! You just completely ignored the fact that there's 2 iodines and 2 nitrates and 2 chlorines and 2 hydroxides. What are you doing? You can't do that. You're violating the law of conservation of mass. If you just had that mindset, then you are thinking correctly. We will pick those up, but we're going to do that at the end. The last thing we're going to do is balance and fix the issues with the missing elements. So just back off, take a second. Let's kind of work this process. Okay, so we made the new pairings. Now the new compounds must be written correctly using their common charges. So here, lead was a +2, and chlorine is a -1. There's got to be 2 chlorines. You just made it worse. Now there's 2 chlorines and only 1. Relax, we'll fix the law of conservation of mass at the end. Use the charges to make the new compounds. Alright, potassium's a +1. Iodine's a -1, so that's the correct formula for this new compound. Zinc is a +2. Hydroxide's a -1. Okay. Magnesium is a +2. Let me get the charges on here for you so you can see them over here. Zinc's a +2, nitrate's a -1, magnesium's a +2, hydroxide's a -1. So anyway, magnesium's a +2, nitrate's a -1, so I better put a 2 here to fix the nitrates. Lithium's a +1, nitrate's a -1, strontium's a +2, chlorine's a -1. If you're wondering where I'm getting these charges from, like how do I know strontium's a +2 and all that, you need to go back and review common charges for the periodic table. That is a must-have for the exam. This is quite possibly the ugliest periodic table I've ever drawn. You know, we have 1, 2, 3, 0, -1, -2, -3. We kind of have that weird column where they meet. You might have a + or -4, and then at the bottom there's some really weird things. And then in the transition areas you have all sorts of Roman numerals. This is my attempt at really bad looking Roman numerals. So you have to have Roman numerals hiding in there. But anyway, so you use the common charges. Where were we? Lithium's a +1, chlorine's a -1, so that's the right formula. Strontium's a +2, nitrate's a -1. I need 2 there. Okay. So, check. New combinations. Check. Write compounds using the common charges. Number 3. Is it soluble or insoluble? We're going to check the solubility rules again. I made those too small. Let me just make that bigger so I can see it. So here we go. Lead chloride. See, all chlorides are soluble. Yay! Oh, there it is, right there. All soluble except for lead. So this is insoluble. So therefore, I'm going to use blue for the states of matter. This is a solid. Okay? Ki. Potassium's an alkali metal, and iodides are always soluble except for lead. And so this is aqueous. And that just made me realize there's actually a mistake here. If lead iodide is insoluble, that should have been a solid right there. My fault. Should have been a solid. I could blame that on Shangra or Hoffman, but that one's mine. Okay, so states of matter for those two. Let's keep going. Zinc hydroxide. All hydroxides are insoluble except for group 1. Zinc is not an alkali metal. And magnesium. Zinc is not magnesium. So this is a solid. Zinc hydroxide. Hydroxides are insoluble. Rule 1. Magnesium nitrate. Rule 2. Nitrates always soluble. No exceptions. There we go. Lithium chloride. Lithium's an alkali metal. Chlorides are always soluble, except for lead, mercury, and silver. Lithium is neither of those, so this is aqueous. Strontium nitrate. Nitrates are always soluble. This is aqueous. Whoa! One of those is not like the other. Which of these 3 reactions is different than the other 2? That's right. 5C, the third one, both compounds are aqueous. If both products are soluble, then everything's still dissolved in the water and no reaction occurred. So all of that beautiful work I just did for this one, scratch it out, no reaction. I don't understand what just happened. Oh my God. So both compounds are aqueous. That means they're dissolved in water. So let's just think about what we did. I have a compound here that's dissolved in water. It reacts or gets mixed with a compound that's dissolved in water and makes something that's dissolved in water and something else that's dissolved in water. So there wouldn't actually be a reaction. Everything's still dissolved in water. Because dissolved in water really means broken apart. So the pieces were broken apart before. The pieces were broken apart, aka dissolved or dissociated in water. They're still dissolved, nothing's actually occurring. 5C is done, no reaction. The other two did produce a solid. Solids, by definition, are not dissolved in water. It sinks to the bottom. Most likely it's more dense than water. Very rarely is the solid precipitate. We call that a precipitate because it falls out of the solution to the bottom. It precipitates or falls to the bottom. So if a reaction has occurred, we need to make sure we balance the reaction so we can follow the law of conservation of mass. Now we're finally going to fix those issues. We use purple. 2 iodines. 1 iodine. Put a 2 there. 2 potassiums. Put a 2 here. 2 potassiums. 2 chlorines. Yay, 2 chlorines. That's a 1, and that's a 1. Zinc. 2 nitrates. 2 nitrates. 1 magnesium. 1 magnesium. 2 hydroxides. 2 hydroxides. So, all done. Just like the single displacement reactions, these questions, had we had time, would have been open-ended. Meaning I would just have given you the reactants and the product side would be blank. But given the time crunch, we're going to cut this down and turn this into a multiple choice style question where I give you 4 different versions of these products. And by that I mean, I'm supposed to put the metal with the non-metal. What's a wrong answer? I shouldn't put lead and potassium together. I shouldn't put chlorine and iodine together. That would be a wrong answer because lead and potassium are both positive. Chlorine and iodine are both negative and they repel each other. So I'm going to work through a couple of wrong answers in the other choices. No reaction, like we saw here, would be an answer. And for A, this is the right answer for A. But I would list as my multiple choice answers, one of them, no reaction, everything's still aqueous. So you're going to have to go through and check the solubility rules. You're going to have to go through and basically do all these steps, but you don't have to memorize the steps. You have to make sure, did he follow the law of conservation of mass? Did he check to see the solubility was correct? Are the new compounds made with metals and non-metals using their charges correctly? All that stuff. But instead of having to generate it all from the top of your brain, you're basically going to pick which answer fits the patterns. Okay, this is a blank page. I don't really have anything to add to it. I wish you best of luck on your exam and have a good day.